Okay, so it's 12:01. Let me just make sure that my mic is working. Looks like it is. So I'm going to get started. We're going to pick up today with 7.1b in the textbook, which is all about describing sampling distributions. Okay, so we're actually going to skip the warm-up for today, but I want to talk about it very quickly. Last time in class, as you guys know, we drew those samples of white and green chips from the bag. And I told you at the end that the true proportion of white chips in the bag was P equals 0.5. Remember that each of your samples created a sample proportion, so we'd call each of those a P hat. Okay? When we did the histogram, we actually noticed that our P hats were centered right around 0.5. So this was actually a pretty good estimator of that parameter. Now, next time when we come in, we are going to do the exit ticket from 7.1a, which is the M&M's activity, which I know some of you are looking forward to. That's going to be fun. I'm going to give you each a sample, which is going to be a bag of M&M's, and I'm going to ask you to calculate a sample proportion for the proportion of orange M&M's out of the whole bag. I do want to give a reminder that this unit ends around January 16th. I am not really expecting guided notes for today from I think it's section 1 would have met today, just because today's guided notes were fairly activity based. If you want to go look into those and try to fill in the blanks as we go, that would be totally fine. And I do encourage it, but I'm not necessarily going to require those handed in. And really the same will go for the other section. If you didn't do the 7.1b notes and hand them in, it's not the end of the world. So we have a couple things to talk about today. We're going to look at unbiased estimators, and we're going to look at sampling variability. We're also going to look at what bias and variability really mean in terms of visual stuff. Then we're going to do a check your understanding or two. And we are actually not going to have quiz 7.1 tonight. Our first quiz is going to be 7.2. Okay, I also want to ask you guys, please make sure we are off today. Make sure you're well rested for tomorrow. Both sections will have class, so let's try to make it a good one. And I think we're both doing 7.2, which is an important day. So please be ready for that. All right. There we go. So let's talk about how to describe sampling distributions. The first thing here is that we need to be able to talk about center. So when we did our sampling distribution, if we had taken all possible samples of size 10 last time really, we would have gotten a sampling distribution that looks something like that red histogram on the bottom left. Okay, it's probably, actually that's more like a dot plot, but we would have gotten something that looked a lot like that. And you'll notice that where is the center of that? Well, it's right on 0.5. So if we had taken a true sampling distribution, meaning all possible samples of size 10 chips, the mean of all those proportions would have been exactly 0.5. So an important point to note here is as long as you're using what's called an unbiased estimator, and I'm sure you guys can imagine what that is. It's some kind of sample or other estimate drawn without bias, right? So we don't have the non-response bias. It's not a convenience sample. It's none of those things that we've talked about before. This is some kind of unbiased estimator, unbiased sample. If we use an unbiased sample, the mean of its sampling distribution is equal to the true value of the parameter being estimated, okay? So, I've talked a lot about polls recently. This is an election year, so I think that's a particularly powerful example here. What would an unbiased estimator look like in a poll? Well, let's imagine that, we get down the road and we have our Republican candidate and we have our Democratic candidate running for president. And a polling company wants to take a sample, take a poll, and see what the percentage of people that's going to vote Democrat is. Now let's imagine just for a moment that maybe the true proportion in the population was 55% of people that were going to vote Democrat. Well, if the polling company uses an unbiased estimator, meaning whatever sampling method it chooses is free from bias, then the average poll should come up with that 55%. Now, like we talked about last time, that doesn't mean and it doesn't guarantee that every poll is going to have a 55% proportion calculated. We do have some variability here. All it means is that the middle of the sampling distribution, the middle of that normal curve, is going to look like 55%. So let's keep moving. And here we're going to actually see an example that talks about sampling with different sample sizes. So I'm going to pull up this website. And what we're going to see here is we have some population, and I'm actually going to modify these things just a little bit. We'll make it like what, 3.99 and 4.93. So what we see is that the population is actually some kind of normal curve, okay? And what I really want to show here is the impact of sample size, because this is our other big thing for today. So with this first example, we're just going to set the sample size to 1, and we're going to do one draw, and I want to see what happens here. So we're just going to pick randomly from this population. Ready? There we go. Okay, so we grabbed one from near the middle. That makes sense. That's highly probable since a lot of the data is in there. We're going to try this again. Again, just one draw, sample size of 1. So this is as if we're polling, one person. We call one person out to see their opinion on something. This really would be closer to a means example, but we're good. Okay, so draw again, and look at that. Okay, so now we draw again. This is as if we did that same poll many times. Okay. Okay, so we're getting some repeats. Okay. Okay. Alright. Okay. I'm actually going to do a bunch of draws at once now. Let's do 20 draws at once, just so we can fill this out a little bit. Okay. So what we have is something that begins, and if I do this more times, let's try 50 times at once. We see something that begins to mimic the shape of the original distribution. Now you guys can see this is an unbiased estimator, so the center of this distribution is actually matching the center of that data set up there. Okay, so as we pick more and more samples, obviously it's going to match that shape better and better and better. Okay, that's all well and good. So we're dealing with an unbiased estimator here. What I want to see now, and you're going to have to remember what this looked like. It kind of matched the shape of that overall curve. I'm going to crank up the sample size. So let's turn it up to, we'll just start with 5. And we're going to do one draw because I want to explain what's happening here. So what you're going to see is a bunch of yellow dots that get averaged to a sample mean. Ready? So we got those 5 dots, they get averaged to the orange, and there's our sample mean. Now we're going to try that again. Another 5 dots, same mean. We're going to try it again. Okay, that one was different. Boom, boom, boom. I think you guys can see what's happening. I'm going to turn up the draws. So now we're going to do 20 draws at a time to fill this out a little bit. Okay, so we're taking a lot of averages. Da-da-da-da-da. Do that again. And again, da-da-da-da. And I'm going to crank it all the way up to 50. Let's do a bunch of draws at once. Okay, so what you may have noticed is that the shape of this sampling distribution is very different than the shape of the population. What happens when we turn up the sample size is that the variability actually decreases by a lot. You don't tend to notice that the spread is as big anymore. Now it's more clustered towards the center. When you think about it, this makes some sense, because it's very unlikely that you're going to have a sample mean that's way out to one extreme. If you have one extreme value in the sample, there should also be some non-extreme values, so the average will be a lot less extreme than that. We're going to see what happens when we turn the sample size up even more. We're actually going to max it out here. So we're going to turn it all the way up to 15. We're going to start with just one draw. so you can see what's happening. So we're taking now 15 data points at once. Okay. Okay. And now we're going to do a whole bunch of draws at once now that hopefully you can see what's going on. And what we're going to see is that the variability decreases even more. So we have a really small amount of variability here, right? Our sampling distribution is restricted to just a couple real outcomes there. Okay, so let's jump back to the PowerPoint because that's really what I wanted to show you guys. And now hopefully you've gotten the memo that if you want to reduce spread, you can take a larger sample. Okay, so we just saw that taking a bigger sample reduces variability. This is going to be good because we actually don't want a lot of variability in our sample, right? We want to be close to that true population parameter. And if we have a bigger sample, then our sample mean or our sample proportion is usually going to be closer to the true parameter. To give you an idea of why this is important, imagine that you're a polling agency and your poll comes back with, variability that's all over the place. This poll says 20% of people are going to vote Republican. The next poll says 80% of people are going to vote Republican. You don't really know where that population parameter is. And more importantly, you have no idea what to say about who's going to win. But now you refine your poll a little bit, you add some more people to it, so you increase that sample size, and now you're getting numbers that are more like, okay, this one says 49, this one says 47, this one says 48. So what you've done there, by increasing the sample size, is you've decreased that variability quite a bit, which is actually allowing you to estimate that population parameter better. Okay, this is all assuming that you've already reduced bias from the poll as much as possible. Okay, so what you're going to see down here is a pretty plain and simple way of putting it. On the left, you have a sample proportion with samples of size 100. You notice that, there's a fair amount of variability in there. Now you crank that sample proportion up to a sample size of 1,000, and that variability really decreases. So the spread really decreases, okay? What you're seeing is that because of that greater sample size, that variability has decreased, and now we're going to be much closer to the population parameter every time, okay? This is just a formal way of putting what I just said. The variability of a statistic is going to be described by the spread of its sampling distribution. This spread is determined primarily by the size of the random sample. Larger samples give smaller spread. Now the spread of the sampling distribution, this is kind of important, does not depend on the size of the population, as long as, this is a rule we've seen before, the population is at least 10 times larger than the sample. Right, so the spread of a poll doesn't depend on how many U.S. adults there are. What really matters is the size of the poll, like the size of the sample that we use for the poll, and also we just need to make sure we're not sampling like 30 million people. At that point, it would start to become a problem, but that's never going to happen. Okay, so let's look at visually what bias and variability tend to look like. And you may have heard these, I think, in terms of the words accuracy, and I can never remember the other one. It's not, I don't think it's sensitivity. Anyway, let's take a look. So in stats, this first one on the top left, we have missed the bullseye with these shots, right? So we think of this as bias, right? Some true mean height of, I don't know, let's say we're talking about the height of capybaras in some country. Capybara is a small animal. I think it's kind of like a rodent. And let's imagine that the true height of these things was like 18 inches, and our sample is giving us back 9 inches every time. That's biased, right? So that's that first bullseye, where the points are all together, but they're very off the mark. Now, the variability is low, which is good, but it's biased, right? Because it's off. It's not on that bullseye. Now let's look at B. B represents a case where we have low bias, because that shot is centered on the bullseye, but we have high variability, right? None of those shots actually hit the bullseye dead on. They're all centered on it. So if we took a bunch of samples, we'd see that they're centered around the mean, but they're just not that accurate. I should say they're too variable, right? We have a lot of variation there. Down in part C, we see the worst possible case, right? There's high bias and there's high variability. This means you have big spread and you're way off the target. This is no good at all, right? This is like, let's say the true proportion of students at Curly that want Saturday classes is 1%. And your poll is coming back 95%, 85%, 99%, 75%. The poll has no idea what the true proportion is, and it's way off the actual population parameter. Okay? So that is a bad one. That is a bad one. The ideal case is part D. Here there's no bias, and there's low variability. Let's imagine that the true average GPA at Curly was 2.8, right? When we take our sample, it's given us back 2.75 as an average. It's giving us back 2.79, 2.82, right? As we take that sample, it's dead on, and it's very close to the true value. So both of those things are beneficial. So again, just to reiterate, bias is going to be that idea that our aim is off, right? Our sample values aren't centered on the population value. High variability, though, means that repeated shots are widely scattered on the target. So repeated samples wouldn't give very similar results. This is like doing the same poll twice and finding that 20% and then 90% of people are in favor of something. It's very variable. It's not very kind of cohesive. It's hard to find the story from that. So the lesson about center and spread here is that if you have a choice of statistics to estimate an unknown parameter, you want to choose one that has no or low bias and minimum variability. Those are going to help you find the story as best you can. Now, unfortunately, very rarely do we get to choose how biased our statistics are and how variable our statistics are. That's just the way of the world. But conceptually, we always want to be thinking about those as ideal. Okay? Let's take a look at this. This is actually something called the German tank problem. So in World War II, the Germans were cranking out about, it looks like from here, about 340, 350 tanks. I think this was a month. Out of their factories, right? The problem that the Allies were having is they had no idea how many tanks there were. They knew there were a lot of them, but they couldn't figure out exactly how many. And of course, you can't very well just go ask the Germans how many tanks they're building. So what they did was they actually collected parts from tanks they destroyed. And they used the model numbers to try to predict how many total tanks there were. Now, using those two numbers, there was a simple method that said, like, okay, let's take this one as the minimum, or extrapolate the minimum and the maximum from this, right? And that's shown up top, above. Other methods of trying to figure out how many tanks the Germans are producing are below. So knowing the true mean, let's think about which of these are probably the best to use in terms of figuring out how many tanks the Germans are producing every month. The first thing we can eliminate is the one at the bottom, partition. I can't remember exactly how this method was done, but you'll notice there's a strong skew to it. So it's a left skew, right? It may be that it kind of centers on that true mean, but the skew makes this a bad sampling distribution, right? We wouldn't want to use this if we had any other options, and we do. I would say probably the next worst is 2 median. What we see here is just a ton of variability, right? It does peak slightly in the middle near the true number of tanks, but not too much variability going on here. It's very hard to tell. Okay, let's look at the next worst here. I think would be mean plus 2 standard deviations. Now, this one is okay, but you guys can see that it's biased, right? The center, which is probably somewhere in here, just doesn't line up with the true center. And we also see a slight left skew here, so that's not going to be super easy to use. The last one I'm going to eliminate is actually twice mean. Now, the reason I want to eliminate this one is we have this pile of points on the right and a pile of points on the left that are probably going to increase variability a fair amount. Okay? So looking at the one that does this the best, max min, what we see is that most of the data is pretty close to the blue line, right? This seems to obey kind of like our 68, 95, 99.7 rule the best out of all these samples. We have a lot of the data close to the middle, which is good. The other thing is that the center of the data appears to be right about that blue line, right? We see about half the points over on the left. We see about half the points over on the right. I don't see a significant skew here. So I would choose max min probably if I had the choice as my best estimator of that population proportion. Okay, so we're going to close here. We're probably a lot earlier than certainly I expected, maybe some of you expected. But the idea here, I want to just reiterate 2 points. First of all, a statistic will be an unbiased estimator if the center of its sampling distribution is equal to the parameter, right? So if the true parameter was a proportion 0.5, then if it's an unbiased estimator, the center of that sampling distribution is also going to be 0.5. We want to keep bias as low as possible. Obviously, we want to shoot for no bias, but anything with lower bias is going to be preferable to anything with higher bias. Secondly, variability, we want to keep that as low as possible. So you're going to hear this mantra over and over and over. Take larger samples. Those are going to make your variability as low as possible. Okay, those are the 2 important points for today. We are going to come back and actually look at the sampling distribution of a sample proportion. I think that is 7.2. And then we're going to look at the sampling distribution of a sample mean in 7.3. So that's kind of our next 3 classes lined up. Be ready for 7.2 tomorrow. That we are going to actually look at some numbers in. Today was a bit abstract. Tomorrow is going to be a little more concrete. Hopefully we will be in school, so we'll get the chance to do that together and also maybe clear up any misconceptions from today. If you did get the chance to watch this, thank you, and have a great rest of your snow day. See you tomorrow.